we had before, the circle of radius 1 at the origin was the unit circle. If I put an angle theta in here, in standard position, that means initial ray along the positive x-axis and counterclockwise positive. The point right here on the unit circle, its coordinates are cosine of theta and sine of theta. Then we can also define, since cosine is x and sine is y, other trig functions too. We could think of this as the ratio in this reference triangle. So this was the reference triangle. It has radius 1 on the circle, so that's 1. Here, if you like, is the x coordinate, and here, if you like, is the y coordinate. You can think of this as x over 1 is cosine and y over 1 is sine, the sides of those triangles. That suggests that we also define the tangent of theta to be the ratio of these sides, y over x. We can define the cotangent of theta to be the ratio of these sides, x over y. The secant of theta to be the ratio of the hypotenuse to this side. Taking into account these can also be negative, so it's not just ratio of triangle lengths, it's the ratio of the coordinates in one. Secant then is 1 over x, the hypotenuse over the coordinate here, and cosecant was 1 over y. And in this way, we have the ratio of all 6 pairs, x, y, and 1. All right, you can arrange those into 6 different quotients, x over 1, y over 1, y over x, x over y, etc. And there's one trig function for each. And then we could do things like this. Suppose we have an angle at standard position. And it has this point on it, 7 minus 24. Suppose we want to find all 6 trig functions of the angle that goes to that terminal ray. We can call that angle theta, let's say. And say find the trig functions of theta. What can we do for that? This is a little trick from what we did last time. I'll also do a little bit of review problems from last time too. But the idea is the unit circle is down here, but we're looking at this point way, way out there. I won't draw it as exaggerated as it should be. We go over plus 7 and minus 24. It's way out here. I don't even know what angle it is, but there's some point way down here. 7 minus 24 on there. How do I find the 6 trig functions for this angle theta? Let me draw it. Hope I didn't draw this too tiny. I was down at the bottom of the board. So there's the angle theta that gets you there in standard position. And we can do this. We can say the corresponding point on the unit circle, if this ray goes through 724, is just these numbers scaled to get a point on the unit circle. So how do we scale these to get a point on the unit circle? The points on the unit circle satisfy that the distance from the origin is 1. So the distance from the origin formula is square root of x squared plus y squared equals 1. So we want, let's divide this one by the root sum square. We'll take 7 squared plus minus 24 squared. And if you work that out, It comes out to be 25. I won't run it on the calculator right now. And so the corresponding point on the unit circle is these just scaled by 25, it turns out. So we can say the point here on the unit circle has coordinates 7 over 25. I'm sorry, it's square root of 25. Let's see. No, that's right. 25. 7 over 25, sorry. Minus 24 over 25. There's the corresponding point on the unit circle. And when you divide these two numbers by their root sum square, you'll find that this squared plus this squared equals 1. It's not hard to prove that. If you want, we can prove it. But what you do to get a point on the unit circle is you divide each number by its root sum square. And now it's just 1 unit out. Once it's 1 unit out, that's the cosine and that's the sine. You just read them off. This must be whatever the angle is. First coordinate is the cosine of it, and the second coordinate is the sine. So now we can say, you need to move the camera just a little bit. That the cosine of this angle, whatever it is 7 over 25, and the sine of this angle, the y coordinate, is minus 24 over 25. Now the others come immediately because tangent of theta is y over x, so we can take minus 24 25ths over 7 25ths. And the 25s cancel since they're both denominators. We say, oh, it's minus 24 over 7. The cotangent of theta, we could do the same. We could say it's x over y. But remember how to do these faster? Once you have the first three, we also had easier the reciprocal identities. That each one of these is reciprocal of one of the others. So cotangent theta could be written as 1 over tangent theta. Just turn this one upside down, minus 7 over 24. The secant theta, recall, was 1 over the cosine of theta. So we turn this one upside down and get 25/7. And the cosecant of theta was the reciprocal of sine. So we turn this one upside down and get minus 25 over 24. There's the value of the 6 trig functions for this angle. So what we can do in general is we can use the point on the circle in these definitions to find all 6 trig functions, but because we have some identities, we can start to find these faster. Those reciprocal identities were quite good. All right. Furthermore, we said, and this is sort of a review, but I want to make sure I make it clear before we get going on the harder problems today. Not only can we find the trig functions given any point on the terminal ray, we can find all 6 trig functions of any special angle. Because essentially we know a point on the terminal ray. What's more, we know the point that's on the unit circle even. The special angle being multiples of 30 degrees, if you do degrees, or pi over 6 radians, if you do radians. Or also any multiple of 45 degrees, which is pi over 4 if you're doing radians. So just look, is that angle a multiple of pi over 4 or pi over 6? Then that's a special angle, and you can find all 6 trig functions easily. For example, suppose I said find, let's say the secant of minus 210 degrees. I wonder what that is. What's the secant of minus 210 degrees? And you can take any angle, no matter how large or how small. Right? said you can find all six. Let's just find this one. What do I do? Remember, I can find the six trig functions by finding a point on the unit circle. So I'll take the unit circle and draw minus 210 degrees. I pull out all whole rotations. There aren't any. I pull out all straight angles. There's one. There is one. And that leaves 30 degrees. If there was a right angle, I would pull that out, but there's not. So I just have one straight angle, taking clockwise because it's negative. Then 30 degrees is 1/3 of a right angle. So I know how to sketch this exactly. And again, it's clockwise since it's negative. I'm going to sketch the minus 180. Then I'm going to break this 90-degree angle into 3 equal parts and go through one of them. There's the terminal ray. There's 30 degrees more. And this between them is the minus 210 degrees. We said what we do is we drop this perpendicular here and get this reference triangle. Right? You take the radius of the circle, the perpendicular drop, and the segment of the x-axis to make this reference triangle. The angle here, always taken positive as the reference angle. Since this was minus 30 going up this way, this is plus 30 degrees. And we must have a 30, 60, 90 triangle. This height here on a 30, 60, 90, since this is the one that fits in the unit circle, we memorized as 1/2. And this base we memorized is square root 3 over 2. It's the 1/2 square root 3 over 2, one triangle automatically. So we know the coordinates immediately are minus square root 3 over 2 plus 1/2. Since we went left and up, x is negative and y is positive. That tells me immediately the sine and cosine. Now I can find all 6 trig functions from those, just like I did here with the point on the unit circle that time. I just say cosine is this number, sine is this number, tangent is this over this, etc. Secant of minus 210 is 1 over the x coordinate, is 1 over minus square root 3 over 2. Is minus 2 over square root 3, right? Just turn it upside down to get the reciprocal. So there exactly is the secant. However, while I will take this on the exam, if you want to compare this with the textbook's answers or the homework answers, what you need to do is rationalize it, multiply top and bottom by square root 3, and write this answer instead. So either one of these answers will be fine on tests and quizzes. So there was finding it by the unit circle. Oops. Now we had a whole lot of identities. I want to add more identities. And we want to apply these to triangles. So we have the quotient identities, the reciprocal identities. The Pythagorean identities were very important ones. We also want to add these, the even and odd identities. Mostly we'll be through with identities after today, but there will be some more as we go along. Quite a few more, but not as many as we've already done. Even odd identities say this, and we're going to derive these from the unit circle. Suppose I have an angle, theta. I know that the coordinates here are cosine and sine. So what are the coordinates down here if I take the angle minus theta? I just go clockwise instead of counterclockwise. Well, when I drop a perpendicular, since I measured the same distance just clockwise here, the perpendicular drops to the same point. So if this is cosine theta, sine theta, and we know because of the angle we took, this must be cosine of minus theta, sine of minus theta is coordinates. You observe that because the x coordinates are equal by dropping the perpendicular, cosine theta must be equal to cosine of minus theta. So observe from the picture, cosine theta equal minus theta, excuse me, is equal to cosine of plus theta. We just proved it on the unit circle. Similarly, the y-coordinate, since you turn through the same angle, just different directions, must be the same except this one's positive and this one's negative. So we now observe that sine of minus theta must be minus the sine of plus theta because the y-coordinates are negative to each other. These are called even and odd identities for sine and cosine because you have to go back to algebra and see what even and odd means. And you find this. In algebra, just general functions, not necessarily trig functions. A function f of x is said to be even if f of minus x is equal to f of plus x. And it has this graphical property. When you go to sketch its graph, whatever it looks like over here is exactly what it looks like over here, just flipped over the y-axis. It gives it symmetry over the y-axis. The reason being that if you take any point here, x, f of x on its graph, right? Then if you go to minus x, the same distance over this side, you have to have the same y-coordinate, right? The y-coordinates are equal when you put in x or minus x. And so this is the point x, f of minus x is the same because f of minus x is equal to f of x. So an even function is always symmetric over the y-axis by its definition. We're going to do graphs of trig functions soon, and what we'll find is that the cosine function has this property. You flip it when you sketch its graph, you can flip it over the y-axis and it lands on itself. But that's the definition, and so we observe from the unit circle, we prove that cosine is even. That's this property from algebra. Also in algebra, a function f of x is said to be odd, if you recall. Everybody forgets these because you don't use them much in algebra. You start to use them when we do the graphs here. F of x is odd if f of minus x is equal to minus f of x. The minus comes out instead of going away. That's the definition of an odd function. Not every function is even or odd. In fact, most functions aren't. Right? If you draw a squiggle in the plane, it's probably not either. In fact, you got to draw it carefully to make it past the vertical line test and just be a function. But this one's neither. What's the property graphically of an odd function? Maybe you remember. If you take any point, here's an odd function. X, f of x on the graph. That point x here. You go over the same distance the other side of the origin to here at minus x, and you should get the y-coordinate at minus x is minus the coordinate plus x. So the point looks like this, minus x, f of minus x. Ought to have minus the y-coordinate, you did it plus x. Right. So what that says is now, x and y are both the negatives of what they were. You have a symmetry through the origin. If this is a distance d on this side, then this is a distance d on this side. Symmetry through the origin, you go the same distance the other side and plot it again with any point. This one here has a sister point over here, right? And so each point has a sister point on the opposite side of the origin. Is the property of an odd graph. It's symmetric through the origin. Let's write that down because we'll refer to it again. That says that when we go to graph these, they're going to have those properties. The sine, you mirror it through the origin, you flip it over and then down like that, and this one will exactly match the shape of this one. Moreover, with our other identities, we can now find that actually all 6 trig functions are either even or odd. So we said functions in general that you draw are neither. Maybe you remember from algebra some even and odd functions like powers of x. If you take an odd power of x, it's an odd function. Its graph actually looks like about like this one I drew. Looks about like that, a little steeper, I guess. If you take an even power of x, it's an even function. And it's not hard to prove, but it's not important for this class. But this one will be, x squared will be symmetric over the origin, x cubed will be symmetric, I'm sorry, x squared will be symmetric over the y-axis, x cubed will be symmetric to the origin. So even powers of x and odd powers of x are even and odd functions, for instance. But every trig function is either even or odd. If, for instance, if I were to add x squared and x cubed, this one is neither. It's got a combination of both. So let's see about the other trig functions. So furthermore, every trig function is either even or odd. For instance, tangent of x. If I take tangent of minus x, do I get the minus coming out like I did here, or the minus going away like I did here, right? Sine is odd. I should have written that on here. Sine is odd. I need to move that over, don't I? What about tangent? Here's where we start to use our identities we had before. If you recall, well, let's say first, tangent is actually odd. The minus comes out. Here's the proof. I'll write these down as identities boxes. One that says cosine of minus theta equals cosine of plus theta. Sine of minus theta is sine of plus theta. Maybe that's off the screen. There's a box for those. Box this one also. This one is because, and here's the easy proof. I like these proofs when they're easy because when you get stuck on the test, you can't remember what's tangent, even or odd. You can figure it out, right? You just take tangent of minus x, and you remember, I should use theta here. I was using theta over there. Let's call it that way. Tangent of minus theta is minus tangent of theta. And then tangent of minus theta, here's the proof, is tangent, recall, is sine over cosine of whatever angle you have. That was our quotient identity from last time. Tangent was y over x, and sine was y, and cosine was x, so tangent is sine over cosine. That's how we proved the quotient identity. But now sine is an odd function, the minus comes out. Cosine is an even function, the minus goes away. Now you got minus sine over cosine, that's minus tangent. There's the proof. So if you forget, you can figure it out, right? Just, sine is odd and cosine is even, the minus comes out and the minus doesn't. That leaves me with 1 minus. We can do some more of these too. I want to do all of these. Once you see the proofs, then these are much easier to remember. Let me know if you can't see me. That screen's kind of hard to see sometimes. Similarly, the cotangent of minus theta is minus the cotangent of theta. It's also odd. There's multiple ways to prove this now. You could use the quotient identity for cotangent just like you did for tangent, or you could use the reciprocal identity at this point. It doesn't matter. Let's use the quotient identity again, just to remind you of the quotient identities. I'm stinking these reviews in as we go along, actually. It's because if you take the cotangent of minus theta, remember cotangent by the reciprocal identity is cosine over sine of whatever angle you put there. But cosine is even, the minus goes away. Sine is odd, the minus comes out. That's minus cosine over sine is minus cotangent. So there's the proof of this one. Furthermore, secant of minus theta is secant of plus theta. Secant is even. Minus drops. How do we prove that one? It's pretty easy. We'll say because secant of minus theta is 1 over cosine of the same angle minus theta. The cosine is even, the minus goes away, it's 1 over cosine. Right? Oh, but 1 over cosine is secant. So there's the proof there. All these you can prove once you do sine and cosine on the unit circle, just by using these quotient and reciprocal identities in terms of sine and cosine. There's the last one here. Maybe I better move the camera a little more. I'm not sure. Oh, that's okay. All right. Finally, the cosecant of minus theta, the minus comes out. It's good to memorize these, but even better to be able to prove them too, because then you'll, in the long run, memorize them. All right. So cosecant is odd. The minus came out. How do we know that? You just continually think of cosecant as 1 over the sine, right? But sine is odd. So the minus comes out. Oh, that's minus 1 over sine is minus the cosecant. There's the proof. Right? Now what those allow us to do, if you want for now, is to avoid doing negative angles like we had to do in that other problem. Let's evaluate again a trig function, and this time let's say find exactly the tangent of minus 120 degrees.
Professor, we are like just barely out of frame.
Okay, thank you. I looked at it over here, I thought it was just reaching, but I just missed it apparently. Thank you. How about this one? We can do it like the last example, but we could more easily do it by this. Sometimes I just don't like to deal with those negative numbers, especially when there's negatives and negatives. So I'm going to instead start off with the odd identity and say I can pull the minus out because tangent is odd. By the way, one thing I meant to mention, it's interesting. You might think odd and even, those are kind of evenly balanced, right? There ought to be 3 trig functions that are even and 3 are odd. Not so. Actually, 4 of them are odd and 2 of them are even the way it comes out. I like to, to memorize these, I like to think cosine and its reciprocal, the secant, are even functions. All the rest are odd. That makes it easy for me to remember. So if cosine and secant are its reciprocal, secant are the even functions, tangent must be odd. I pull the minus out. So maybe that'll help you too. I don't know. So now I need the tangent of minus 120 degrees. And I just have to deal with a positive angle. Sometimes that's easier just to deal with positive numbers and not have to worry about those. So let's see what 120 degrees look like. 120 degrees is a right angle plus a third of a right angle, right? So on the unit circle, there's my right angle. Break that into 3 equal parts. There's my third of a right angle. There's 120 degrees. If this is a 30-degree angle here, we said, that leaves a 60-degree angle here for my reference triangle. If it's a 30, 60, 90 triangle, then this side is square root 3 over 2. This side is a half, and this is 1. Tangent, remember, is y over x. So it's the coordinate here. Let's write the coordinates because these are the sides I'm going to write on the triangle. But up here, I'm going to put the coordinates. Minus a half since I went left, plus square root 3 over 2 since I went up. So it's minus y over x. Oops. Yeah, there's minus square root 3 over 2 over minus a half. And now I observe these minuses cancel. And the 2's cancel, since they're both denominators. And I just get square root 3. So you don't have to do this. You can draw the angle counterclockwise too. I'm sorry, clockwise too, and do minus 120 degrees. Or you can pull the minus out, take the tangent of this positive angle, and then sometimes that's easier. suppose I want to now find the secant of minus pi over 3. This is where it really shines, this method. If I want to find the secant of minus pi over 3, wait a minute, secant is even. All I have to do is find the secant of plus the pi over 3. So I just draw this right into the first quadrant now. This is where it really helps you, I think, drop the minus. Pi over 3, you just have to recall, is 2/3 of a right angle. Or you can remember it's 60 degrees, either way. So when I drop the perpendicular, this is a 30, 60, 90 triangle. And this is a half, this is square root 3 over 2. And the secant of this one is 1 over the x-coordinate, is 1 over a half. It's exactly equal to 2. There's the secant of pi over 3 using the even odd identities. Well, one last group of identities. Like I say, there's a lot of these sections. Are the cofunction identities. I put these last because these are in some sense the least important. Those even odd identities we're not going to use much for now except to avoid negative angles sometimes. But in the long run, they will be real nice for graphs and also for proofs. These will hardly use the rest of the semester, but you do need to see them because they do come up in practice a little. For any trig function, you might say, why is this one sine and this one's cosine? This one's tangent, this one's cotangent. This is one reason why. If you take the sine of theta, it's always equal to the cosine of pi over 2 minus theta. This is most easily seen in the first quadrant. Or even better, I like it with triangles that we're about to do. But if I take this angle theta and I drop the perpendicular, we'll just do this in the first quadrant here. Then this is x and this is y. And if you take the sine of theta, it's the y coordinate here. What is the cosine? You know, let's draw this in degrees for now. 90 degrees minus theta. If this is theta, what angle is this up here? That's 90 minus theta, right? Now, if you were to draw the angle 90 minus theta over here, this would be the same triangle, right? Now, this is the angle 90 minus theta put in this position. So this is actually the same triangle as this one. I guess we can call it a congruent triangle since it's in a different spot. So this is congruent to this one. And that means that this one is now a half, and this one is square root 3 over 2. So if sine theta is the y coordinate, that's the same as the x coordinate on this triangle flipped this way. So it's cosine of this angle here, which is 90 minus theta. I'm going to do this again when we do triangles, and this will be a little easier to follow. But since we haven't got those yet, and this book introduces these now, I'll go ahead and do it this way. Because if you take the triangle and flip it over this way, the x and y coordinates interchange, and the cosine of this angle is what was the y coordinate of this angle. The x coordinate for this one is what was the y coordinate for this angle. And so that's the derivation of the unit circle, a little harder than the other way. And then you can do it the other way too. If you take the cosine of theta, it's equal to the sine of 90 degrees minus theta. All right. Cosine would be the x coordinate here. When you flip the triangle over here, it's the y coordinate on this one. It's the same triangle turned the other way. And so you have cosine theta is the x coordinate on this one. Well, that's the y coordinate on the other one. Sine of the other one. So they're you don't have to remember which way it goes. You can do it either way. The sine is the cosine of 90 minus, and the cosine is the sine of 90 minus the original angle. Right? So their co-functions, sine and cosine, have this identity. Furthermore, I'll state without proof, although you can do it just as well, it's similarly. If you take the tangent of any angle, it's the same as the cotangent of 90 minus the angle. The cotangent of any angle, correspondingly, is the tangent of 90 minus the angle. So they're co-functions of each other. Tangent and cotangent go together, sine and cosine go together, secant and cosecant go together. The secant of any angle is the cosecant of 90 degrees minus the angle. The cosecant is the secant of 90 degrees minus the angle. Well, there it is. There's all the identities you need to memorize for now. And these are the least important. But you will see some problems in there, like this. If the sine of an angle is equal to minus 3/5, actually, let's do the problem right here. Oh, there we go. They wrote it this way. They wrote cosine of 34 degrees is the sine of what degrees? And fill in the blank. How about that? According to the identity here, the cosine of an angle is sine of 90 minus the angle. So this must be 90 minus 34 degrees, right, which is 56 then. So 56 goes in the blank. If I ask you, similarly, you have to be able to do these in radians. What's the cosine of pi over 3? That's equal to the sine of what angle? That goes in there. In radians, 90 degrees gets replaced with pi over 2. So this one, instead of 90, put pi over 2 minus whatever angle was here. And the cofunction identity becomes, well, pi over 2 minus pi over 3. How do I subtract those? Remember, this is very important for this class, actually. We need to put them over a common denominator. What's the least common multiple of 2 and 3? That'll be my least common denominator. Right, well, they have no factors in common, so it says 2 times 3 is 6. So I need to put these each over 6. I'll multiply this one top and bottom by 3 and get 3 pi over 6. I'll multiply this one top and bottom by 2 and get 2 pi over 6. 3 pi over 6 minus 2 pi over 6, you subtract the numerators over the common denominator. Pi over 2 minus pi over 3 is pi over 6. This is going to come up a lot during this semester. But the cosine of pi over 3 is actually equal to the sine of pi over 6 by the cofunction identity, because these two add up to a right angle, pi over 2 or 90 degrees. Try one more of these. Hope that was on there. That wasn't maybe far enough, was it? Huh. Suppose I want to take the tangent of pi over 4. That's equal to the cotangent of what? What goes in this blank? Well, according to this identity we had here, the tangent of any angle is cotangent of 90 minus the angle, but you replace 90 with pi over 2. So this is pi over 2 minus the angle that you have. Right? If this is theta, This is pi over 2 minus theta, a 90-degree angle minus theta. So it's pi over 4, pi over 2 minus pi over 4. You put them over a least common denominator. Well, these are both divisible by 4, so you just have to multiply the first one top and bottom by 2 and call it 2 pi over 4. This one is then pi over 4 still, and they have a common denominator. You can subtract the numerators. 2 pi minus 1 pi is pi, all over 4. So actually, tangent of pi over 4 is equal to cotangent of pi over 4. How about that? So try those on the homework. And that'll finish up our identities for now. Maybe we just need another problem here or two on reviewing these identities. So here's some review of identities now that we've finished them all. I don't want to write them all out again. I'll just recall them as we go. Let's try this. If cotangent of theta, I'm sorry, cosine of theta is 1/2, find cosine of minus theta. What is it? Now remember the even identity. Cosine of minus theta, the minus goes away, and so it's also 1/2. How about that? If tangent of theta is minus 1.4, suppose I want to find cotangent of minus theta. How about that? It's a little trickier than on the paper, actually. Well, cotangent is the reciprocal of tangent of the reciprocal identity, right? Tangent is an odd function, so the minus comes out. And tangent is minus 1.4, so it's 1 over minus 1.4. It's just 1 over 1.4. Really, you want to simplify that. Let me see, get my calculator just for a second. Okay, so we can rewrite this one. As approximately 0.7143. Is approximately what the cotangent would be then. Now we can also do some proofs with these identities. We haven't tried that yet. What's going to come up in chapters shortly is simplifying these trig expressions. It's very common in science to get a complicated trig expression that simplifies. So let's try a little bit of that now. Suppose I said on the first exam, simplify this expression. Cosecant theta times tangent theta. How does that simplify? One nice thing that's true in a lot of these identities, if you're stuck, try writing them all in terms of sine and cosine. So I'm going to make this suggestion. Write cosecant as 1 over sine using the reciprocal identity. Write tangent as sine over cosine using the quotient identity. If you write these all in terms of sine and cosine using the reciprocal and quotient identities, the signs cancel, right? Top times top over bottom times bottom, these cancel. You get 1 over cosine. That's just called the secant. So these really help you to memorize the identities when you see those. Okay, I think that maybe just one more problem here. How about this one? We didn't get to the hardest problem actually for last time. If tangent theta is equal to 12/5 and theta is between 0 and pi over 2. Actually, I'm going to change this a little bit. Pi over 2, pi.
Professor, we are just out of frame again.
Okay, thank you. And 3 pi over 2. Find all the trig functions. We said last time, given one trig function and a quadrant, this tells you the quadrant, right? You can find all 6 trig functions that are that related. Now this one is the hardest one when you're given a tangent or a cotangent. If you're given a sine or cosine, it's easier to start off. Here's how I recommend doing this one. All right, tangent theta equals 12/5. Divide top and bottom by the root sum squared. Take square root of 12 squared plus 5 squared comes out to be square root of 169 is 13. And divide top and bottom by that, right? This is 12 over 13 over 5 over 13. And once you do that, this becomes a point on the unit circle. Remember, when you divide the two numbers by the root sum square, they now lie in the unit circle. And so this one, since tangent is sine over cosine, might be the sine. And this one might be the cosine because it's a point on the unit circle. But there's one other case. If you take minus this one over minus this one, that also lies on the unit circle and has the same ratio. So it might be minus 12/13 over minus 5/13. This might be the sine, and this might be the cosine. This is going back to that concept we had at the beginning here, that the tangent theta can be y over x, and so it might be that y is 12 and x is 5, and you've got a point on the terminal ray here. And then there's a unit circle way down here. Or it might be that this is the point minus 12 and minus 5, and that makes the ratio 12/5. But when it tells you tangent is 12 over 5, it's telling you that there's a point on the terminal ray, either 5/12, or minus 5, minus 12. So what we're going to do is find these 2 points that are on the unit circle by dividing these 2 numbers by the root sum square and getting a point on the unit circle. Now, once I do that, I say there's 2 possibilities where the ratio is 12/5. This could be the sine, this could be the cosine, or this could be the sine, and this could be the cosine. Which is the case? Well, we're in quadrant 3. In quadrant 3, the x-coordinate cosine is negative and the y-coordinate sine is negative, so it must be this one. So we'll scratch out this one and say it has to be in quadrant 3 because, and that makes x and y negative. Okay? So it's this one over here, not this one up here. And we'll say from this we observe the sine of whatever angle it is. We don't even know what angle goes to 5/12. Sine must be the top one, minus 12/13, and cosine must be the bottom one, minus 5/13. Once you have sine and cosine, you can just use reciprocal identities and cosine identities to find all the rest. And you're welcome to use the identities however you like. Sometimes some people like some identities better than the others. So we can now find, we have sine, cosine, and tangent. We can find cotangent. And there's 2 ways to do it, right? One, you can write the quotient, at least 2 ways. You can write the quotient identity, just take cosine over sine, but even easier, once you have sine, cosine, and tangent, why not just take all three reciprocals, right? So if tangent was 12/5, cotangent is its reciprocal, 5/12 immediately. If cosine was minus 5/13, secant, being its reciprocal, is minus 13/5. Just turn this fraction upside down. If sine was minus 12/13, cosecant must be that one upside down, must be minus 13/12. So once you have the sine, cosine, and tangent, the other three write their reciprocals. But this is the hardest one, the tangent. Given a tangent or a cotangent, you can divide top and bottom by the root sum squared, plus or minus, and get sine and cosine, and then you can get the rest of them. There are other ways to do this also. You might prefer if you have the Pythagorean identity. Once you know tangent, you can know secant from the Pythagorean identity and then figure the others. And if you like one of those ways, you're welcome to do it. And finally, let's do a slightly simpler one. Let's see it on here. All right, let's do this one. If cosecant is -4 and theta is in quadrant 4, find the other trig functions, sine, cosine, etc. Just like we did on this one. But this time I'm doing cosecant. I only need to do that root sum square trig for tangent and cotangent, it turns out. Because this one, I can just say immediately, sine is the reciprocal of the cosecant using the reciprocal identities, is minus a fourth. I just turn this one upside down.
So we are out of frame again, just so you know.
Yeah, I knew that and I forgot to fix it. Thank you. So if you know the cosecant, you immediately know it's reciprocal. Now, how can I get cosine from sine? Remember this one? The Pythagorean identity solved for cosine. If you know sine, cosine is immediately plus or minus square root 1 minus sine squared. This one we haven't got to today, we just did it last time. But once you know sine, you can immediately write this for cosine. The Pythagorean identity, just to remind you, was this: sine squared plus cosine squared equals 1. We derived it with the Pythagorean theorem, so it looks like the Pythagorean theorem. A squared plus b squared equals c squared. You can think of that as squared if you want. Came out of the Pythagorean theorem in the unit circle. This one solved for cosine is by subtracting sine squared over here and taking the square root, is that cosine is plus or minus the square root 1 minus sine squared. And if you subtract cosine squared over, so sine squared is 1 minus cosine squared and square root both sides, you find that sine theta is plus or minus square root 1 minus cosine squared theta. So recall this is the Pythagorean identity for sine and cosine. And these are that Pythagorean identity solved for sine and cosine. I'm going to apply this one right here, the identities from last time, and say, all right, is it plus or minus? That's where we use quadrant 4. In quadrant 4, the x-coordinate is positive. Cosine is the x-coordinate. So you take cosine positive. But quadrant 4 forces that to be a positive. Right? So it's positive square root 1 minus sine squared, but sine is minus a fourth. And now you have to do your fractions here. This is 1 plus a 16th, right, is the square root of, well, 16 sixteenths and 1 16th is 17 sixteenths. And then I want you to reduce that, right, because 16 is a square. You can say it's the square root of 17 over 4. There's cosine. Now, once you know sine and cosine, you know how to do all trig functions immediately. All right. I guess I can get rid of this one. Now immediately the tangent of the angle is sine over cosine is minus a fourth over square root 17 over 4. These are both denominators, so they cancel. And you get minus 1 over square root 17. I won't rationalize it this time because what's now easier for calculating cotangent is just turn this one up and say it's minus square root 17 by reciprocal. The secant is the reciprocal of cosine. You just turn this one upside down and call it 4 over square root 17. Now the cosecant, you turn the sign upside down. Oops. We already got cosecant. Cosecant was given, so you just get minus 4. Okay. So there's all 6 trig functions. Given 1 and a quadrant. All right, so that finishes the section. You should try all the problems here. I gave you most of them last time, I think, to look at, but do all the problems on 5.3. I think it's combined 5.2 and 5.3. And see if you have any questions for next time. Yeah. Finish. Homework 5.2, 5.3 on the UCO supplement.